Hello, Physics 20s. In today's lesson, we are going to continue our discussion of the gravitational force of attraction between two objects. Although this time around, we're going to look at objects that are subjected to more than one gravitational force. If we're subjected to more than one gravitational force, there will be a net gravitational force acting on the object. And we'll continue to use Newton's universal law of gravitation to do this. No need to state the learning outcome because it is just identical to the one from before, again applying Newton's universal law of gravitation. Okay, so first example, I want to determine the net gravitational force acting on sphere 2 if m1 is a kilogram, m2 is 2 kilograms, m3 is 3 kilograms, and I'm given the distance between my objects. Okay, so we're interested in sphere 2. So I'm going to start off by drawing a Freebody diagram of sphere 2. Now, what I want you to do for a moment is just pretend like sphere 3 does not exist. Okay, it's not part of the system. Only 2 and 1 exist. If I'm sphere 2, what kind of a force would I feel in relation to number 1? Well, object 1 would exert a gravitational force on 2 that would make it attract towards it. Therefore, if I'm sphere 2, I feel that gravitational force that's going to pull me towards the left. And we'll call that F, G, 1, 2. Gravitational force between objects 1 and 2. Now let's pretend that number 1 doesn't exist. And let's look at the interaction between 2 and 3. If I'm object 2, what kind of a force would I experience in relation to 3? Well, object 3 would exert a gravitational force on 2 that wants to attract it. So that's going to be towards the right. On a Freebody diagram, you're supposed to communicate which force is bigger. So which force is going to be bigger? The force that pulls 2 towards 1 or 2 towards 3? Well, universal gravitation tells me that Fg is gm1, m2 over r squared. There's a couple of important things here. So Fg is directly proportional to the product of the masses, and it is inversely proportional to the distance between the objects squared. Okay, so let's look at this. How do 1 and 3 differ? Well, object 1 has a lower mass than object 3. So the first part of the equation would tell me that the force of attraction towards 3 would be bigger because mass 3 is larger. The other one tells me that if the distance between them is smaller, the force is bigger. And if you look here, the distance from 2 to 3 is 1 meter in comparison from 1 to 2, which is 2 meters. Therefore, that gravitational force between 2 and 3 wins on both accounts. And it wins because mass 3 is larger, and it also wins because the distance, which obviously is not drawn to scale here, is smaller. So I'm just going to exaggerate that vector on the FBD here. So we'll call this FG2, 3. Just beware, because I have multiple objects, I'm going to have to add a lot of subscripts to my equations just to distinguish different things. What I'm going to do now is I'm going to calculate the magnitude of these two forces using universal gravitation. So Fg, 1, 2, would be equal to G, m1, m2, all divided by r squared. Let's plug the numbers in. Our gravitational constant is 6.67 times 10 to the negative 11 newtons times meter squared per kilogram squared. Multiply this by mass 1, which is 1.00 kilograms, times mass 2, which is 2, 0.00 kilograms. And then divide this by the distance, 2.00 meters squared. So that gives me Fg between 1 and 2 is equal to, and I got a value. Let's add one more significant digit than we need, 3.34 times 10 to the negative 11 newtons. One other thing, for the R value, we should clarify what it is the distance between. So I'm just going to add 1, 2 here. So R12 means a distance between 1 and 2. It does not mean R12. Let's also calculate Fg23. So Fg23 would be equal to G. Now, we can change the subscripts on the universal gravitation equation to match the masses we're dealing with. So instead of saying M1, M2, let's say M2, M3, because that's the gravitational force I want to find between those two masses. Divide this by R squared, and we'll add 2, 3 here to indicate it's the distance between 2 and 3. Plug the numbers in, so you got 6.67 times 10 to the negative 11 newtons times meters squared per kilogram squared. Multiply by M2. M2 is 2.00 kilograms. M3 is larger, 3.00 kilograms. Divide this by that smaller distance, 1.00 meters squared. And then I get Fg23. We already know it's going to be a value that's larger. And to 3 significant digits, I get 4.00 times 10 to the negative 10 newtons. Okay, so I've got these two gravitational forces. And now I'm going to figure out the net force that's acting on sphere 2. So first of all, let's pick a direction we want to be positive. So I'm going to say I want right to be positive. And I'm going to calculate the net, so sigma, gravitational force acting on object 2. Sigma Fg2 means the net gravitational force acting on mass 2. Okay, now let's look at the free body diagram and expand this. We're not going to worry about the mass acceleration part of the equation. Yes, there is some acceleration if you release these guys from rest, but we're just going to worry about expanding the sigma F part. Okay, so if we look at the FBD, Fg12 points towards the left, therefore it's negative. Negative because it points towards the left. Fg23 points towards the right, therefore it's positive. Okay, now it's a matter of just plugging the numbers in. So Fg12 is 3.34 times 10 to the negative 11 newtons plus 4.00 times 10 to the negative 10 newtons. And then that's going to give me the net gravitational force acting on object 2 is going to be a positive number. And now let's go to 2 significant digits. 3.7 times 10 to the negative 10 newtons. And then brackets, we'll also clarify what the positive means. The positive, according to our sign convention, means it's towards the right. This one isn't too bad because everything is in a straight line. If everything's in a straight line, we're dealing with a one-dimensional problem. Example 2, the masses are not in a straight line. So now we've got a two-dimensional problem, and as we know, two-dimensional motion is always more difficult to analyze than one-dimensional motion. Maybe not more difficult, but definitely more tedious. And you're definitely going to see that in this example here. All right, in the diagram shown below, masses 1, 2, and 3 are all the same mass. Okay, so we've got that at least. And the distance between those objects from 1 to 2 and 2 to 3 is also the same. So that's good that we've got some constants here. And I want to calculate the net gravitational force acting on sphere 2 and then sphere 1. It's going to be easier to do it on 2 than 1. Now, before I get into this, I'm going to do some preliminary calculations that are just going to save me a little bit of work later. The first thing I'm going to do is I want to calculate the distance between 1 and 3. So we'll call that R1, 3. To calculate that, we just use Pythagorean's theorem. So that would be R13 is 2.00 meters, all squared, plus 2.00 meters, all squared, and then R13 would be equal to, let's go to 3 significant digits, 2.83 meters. Now, I also want to calculate, I'll do this in a different color. I also want to calculate this angle. We'll call that theta, the angle theta. Okay, now I'll show the work inside the triangle here. You might recognize right away that both sides opposite and adjacent are the exact same sides. And if that's the case, it's going to be a 45-degree angle, but not all of our problems are going to be like that. So I'll just show the work for doing this. In fact, let's do it outside here. Theta would be equal to the inverse tan of side opposite, 2.00 meters, divided by 2.00 meters, and that gives me a 45-degree angle. I'm going to want to make more use of this angle, though. So let's draw at this point here a horizontal line that kind of just goes a little bit across. I like to have my angles relative to the horizontal. So if this guy's 45 degrees, this would be a right angle. Therefore, this would also be 45 degrees. We'll make use of that in a moment. Okay, what I'm going to do is I'm going to calculate the gravitational force magnitude between every possible combination of masses. I'll do between 1 and 2, 2 and 3, and 1 and 3. Okay, let's do 1 and 3 first. So I'll say Fg 1, 3 is equal to G M1 M3 divided by R1 3 squared. Let's plug the numbers in. Gravitational constant 6.67 times 10 to the negative 11 newtons times meter squared per kilogram squared. Multiply by M1, it's a 1 kilogram mass. Multiply by M2, also a 1 kilogram mass. Divide this by the distance between them. We calculated that from Pythagorean theorem. So that's 2.83 meters all squared. Then I get the magnitude of the gravitational force between 1 and 3 would be, let's add due to 3 significant digits, 8.33 times 10 to the negative 12 newtons. Okay, so that's one important value. Now let's go between 1 and 2. So Fg1, 2 would be equal to G M1 M2 divided by the distance between 1 and 2 squared. Plug the numbers in. 6.67 times 10 to the negative 11 newtons times meters squared per kilogram squared multiplied by m1, 1 kilogram. The only thing that's changing here is the distance. And the distance is smaller. Therefore, that force is going to be bigger due to that inverse squared relationship. Okay, when we calculate Fg12, we would get a value of 1.67 times 10 to the negative 11 newtons. Just want to point out, look how small these forces are. This is why the gravitational force between like normal objects is just not that big of a deal. It's different if one of your masses is a planet, but otherwise the gravitational force between just regular objects is so insignificant it may as well not even be there. Okay, the other one we need to calculate is Fg23, but we don't need to actually calculate it. Fg23 is just equal to Fg12 because all of the numbers are the same. Specifically, say because m1 equals m3 and r12 equals r23. Okay, so we've got these three numbers that are going to be very useful for us in solving the remainder of the problem. And again, I just did the prep work in advance because it's just going to save me some steps later on. I am going to have to make use of all three of these values. Depending on the problems you solve, you might not need to calculate all three. It just depends on what object you're being asked to figure out the net force on. Okay, so let's figure out the net force on 2. So we're going to start off by drawing a free body diagram of number 2. Now, if you're in the place of sphere 2, let's pretend that number 3 doesn't exist for a second. And then let's look at how 2 interacts with 1. So if I'm object 2, what do I want to do in relation to 1? Well, the gravitational force is always attractive, so I want to go towards it. So we call that Fg12. If we pretend like 1 doesn't exist and identify how 2 would interact with 3, it would want to attract to it, so we would have Fg23. By the way, this little process where I'm pretending like 1 mass doesn't exist, and I'm looking at how like 2 would interact with 3, and then I pretend like 3 doesn't exist, and I want to see how 2 interacts with 1, and I kind of put them together at the end. That's called the principle of superposition. Okay, we've already calculated these forces. Now, what I need to do here is to get the net force on sphere 2, I need to know what the net force is in both the x and the y direction. And then when I know what it is on both the x and the y direction, I can figure out the net force and express that as a two-dimensional vector. Okay, so let's figure out what the net force is in the x direction. So let's assume that right is positive. I'm going to find the sum of my gravitational forces acting on mass 2. It's not even a sum here. There's only one force acting on the object in the x direction. So we'll say sigma Fg2x. And that is just equal to positive Fg23. And Fg23 was 1.67 times 10 to the negative 11. So 1.67 times 10 to the negative 11 newtons. Now let's figure out the net gravitational force acting on 2 in the y direction. So assume up is positive. Find the net gravitational force acting on 2 in the y direction. Look at the FBD. It's not even a sum, it's just one force. It's FG1, 2, it points up, therefore it's positive. Not only is it positive, it has the same magnitude as the force value in the x direction. So that would be positive 1.67 times 10 to the negative 11 newtons. Now I need to take these two values and construct a resultant vector diagram to get the net force. We're going to take these vectors and use them as directions on a road map. So positive x direction means draw a vector that goes towards the east, and a positive y direction, draw a vector that goes towards the north. Okay, so my resultant vector diagram. Okay, so from some just random starting point or reference point, we'll draw a vector that first goes east, and it does it by 1.67 times 10 to the negative 11 newtons. And then we add our next vector, tip to tail. So then I would add this vector going north, 1.67 times 10 to the negative 11 newtons. And then what I want here is the resultant vector. So the resultant vector is from the tail of the first vector to the tip of the last one. And we want two things. We want to know what is the hypotenuse of the triangle, which I'm going to call FG2, the net gravitational force on 2. And I also want to know this angle so I can express it as a two-dimensional vector. Now, I've already used the variable theta for the calculation in this part, so I'm just going to relabel it as a different angle variable. I'm going to choose, you write down theta 2 or theta 3. I'm going to choose the Greek letter alpha. Okay, so to get sigma FG2, we need the magnitude, and we need to know what that angle is. So the magnitude, just use Pythagorean's theorem. So the magnitude of sigma FG2 would be equal to 1.67, sum of the squares, times 10 to the negative 11 newtons squared, plus 1.67 times 10 to the negative 11 newtons, all squared. Take the square root of that, and then we're going to get a value. And this is part of the final answer, so now we'll start going to significant digits. So this magnitude would be 2.4 times 10 to the negative 11 newtons. On the resultant diagram, you might recognize again that the adjacent and opposite sides are the same length, which means that it'll be a 45-degree angle again. But not all examples or not all problems are going to be like this. I'll just show the work for calculating it. So we have theta is equal to the inverse tangent of side opposite, which is 1.67 times 10 to the negative 11 newtons divided by 1.67 times 10 to the negative 11 newtons. And yes, it gives you a 45-degree angle. Okay, now we put the magnitude and the direction together in a statement, which would just tell me that sigma FG2, so the net gravitational force acting on object 2, is going to be 2.4 times 10 to the negative 11 newtons at an angle of 45 degrees. And if we express it in compass notation, it'd be north of east. Or if you wanted to express it in RCS notation, we could just express it as 45 degrees. You could also express it as 45 degrees east of north if you wanted to use the alternate compass notation. Okay, so like I said, it's a little bit tedious. Now, B is even more tedious in comparison to part A. So B wants us to figure out the net gravitational force that's now acting on sphere 1. So to find the net gravitational force, we want to start by drawing a free body diagram. So let's draw number 1. Let's pretend 3 doesn't exist for a second. So we're going to apply the superposition principle. If 3 doesn't exist, what does 1 want to do? It wants to attract towards 2. So that'd be a gravitational force that's straight down. So we're going to call that FG 1, 2. And then if 2 doesn't exist, what does 1 want to do? It wants to attract towards 3, albeit at an angle this time. And it'll be an angle with a force with a smaller magnitude. We'll call that FG 2. Oh, FG 1, 3. My bad. Let's erase that. FG 1, 3. Okay, now the reason this one's a bit more tedious than the other one is because the one force FG 1, 3 is not in a horizontal or vertical plane. It's at an angle, and then what we want to do is, if it's at an angle, we want to break it into the vector components. So I'll break it into the components. We'll do this with blue. So do my horizontal component first. So this goes across, and we'll call this FG 1, 3 X. Vertical component goes down. We'll call that FG 1, 3 Y. And this is why at the start of the question I calculated that one angle. If we go back, this angle at the very top here relative to the horizontal, because I need to make use of that angle once I got into the vector components of the FG 1, 3 vector. So we know that this angle here is 45 degrees. Okay, so we're going to do the same thing now. We need to calculate the net force in the x direction and the net force in the y direction. Okay, so let's start in the x direction. So we'll say, let's make right positive. And I want to find the sum of the gravitational forces on object 2 in the x direction. If you look at the Freebody diagram, there is only one force in the x direction. That is the x component of FG 1, 3. It points towards the right, therefore it's positive. So you have positive FG 1, 3 X. If we break that component apart, it would then be FG 1, 3 multiplied by cosine, as long as I keep that angle relative to the horizontal, 45 degrees. Okay, let's plug some numbers in. So FG 1, 3 is 8.33 times 10 to the negative 12 newtons. Again, I did that calculation on the first slide for this problem. Times cosine of 45 degrees. And that's going to give me the net gravitational force in the x direction is equal to positive 5.89 times 10 to the power of negative 12 newtons. And the positive means the force is towards the right. Okay, so we're going to make use of that force momentarily. The fact that it's this magnitude and it points toward the right. But now we need to go to the y direction, figure out the net force there. Okay, look at the Freebody diagram. Let's be clever about a direction we want to be positive. So you don't always have to say up and right is positive. We can choose whatever direction we want to be positive. Look at the Freebody diagram. Both y forces, FG 1, 2 and FG 1, 3 y, they both point down. So let's make down the positive direction. Doesn't matter which direction you make, positive or negative. It's still going to give you the same result. Okay, let's find the net gravitational force acting on 2 in the y direction. If down is positive, that would be, so we actually do have a sum of forces now. So FG 1, 2 points down, therefore it's positive. FG 1, 2. And the y component of FG 1, 3 points down. So we have positive FG 1, 3 y. If we expand that a step further, that would be FG 1, 2 plus FG 1, 3. And we're dealing with the y component, which is on the side opposite of our angle, so that's the sine angle. Let's plug numbers in now. So FG12 is 1.67 times 10 to the negative 11 newtons, plus FG13 is 8.33 times 10 to the negative 12 newtons, multiplied by sine 45 degrees, and that's going to give me my net force is in the y direction, 2.26 positive, times 10 to the negative 11 newtons, and down is positive according to our sign notation. Okay, so then we have this part. Now that we have the net force in the x and y direction, we can construct a resultant vector diagram to get the overall net force. So my resultant use these as directions on a roadmap. So this is going to tell me to go right and then down. So I go right. I'm not drawing these to scale, by the way. The math will do the work for me. Okay, so this would be 5.89 times 10 to the negative 12 newtons. And then we add that next vector tip to tail, which is then going to be down. Just be aware that the down magnitude is bigger than the right magnitude. But again, I'm not drawing it to scale. 2.26 times 10 to the negative 11 newtons. And then we want the resultant. Resultant from start to finish. So I want the hypotenuse, which would be sigma FG. We're doing 1. Whoops. Sigma FG1. Let's fix this. This should be sigma FG1x. This should be sigma FG1y. Yeah, that's correct now. 1x, 1y. We want sigma FG1. Okay, we also need this angle here. And it's going to be at different angles. Let's pick another letter of the Greek alphabet to represent this. I'll pick the letter gamma. So it's like a vertical alpha symbol. Okay, so let's calculate this. So the magnitude, sigma FG1, would be equal to, take the sum of the squares and the square roots, that'd be 5.89 times 10 to the negative 12 newtons all squared, plus 2.26 times 10 to the negative 11 newtons all squared. And then that would be equal to, as a part of your final answer, so we can go to significant digits now. So I get 2.3 times 10 to the negative 11 newtons. Let's calculate gamma. So that would be, gamma is the inverse tangent of side opposite is 2.26 times 10 to the negative 11 newtons. Divide this by side opposite, 5.89 times 10 to the negative 12 newtons. Then I'm going to get an angle, let's just go to a whole number, of 75 degrees. Let's put this together now. We can say the net gravitational force on 1 would then be equal to 2.3 times 10 to the negative 11 newtons at 75 degrees south of east. Or we could write it in RCS notation just by going 360, subtract that angle. So we could also write it as or at 360 minus 75 would be 285. Or the other way of writing it in the compass notation would be 15 degrees east of south. Okay, so that's it. Unfortunately, yeah, it is a tedious process, as it is any time you're dealing with like two-dimensional vectors. And you can practice this work on an assignment called the Net Gravitational Force Hand-in assignment. And I will talk to you next time we get into a discussion of gravitational fields.